Okay, we're now going to start to look at the motion of charged particles in a uniform electrical field. So it's very similar to that of a mass in a uniform gravitational field. You've done questions already where you're looking at gravity, where there's the Earth, and we know there's a uniform gravitational field giving you acceleration due to gravity downwards there of G equal to A is equal to 9.8 or minus 9.8. And you can put a mass there and work out how long does it take to hit the ground, or you can fire one in sideways and look at that parabolic motion and answer questions like what's the time in the air, what's the range, what's the final velocity, and so on. So we're going to try and do the same thing here with a uniform electrical field, which will be created by two oppositely charged parallel plates. In this case, I've got one at a potential of 5,000 volts plus, and one is the Earth here, 0 volts. But I could have equally given this the same value by doing this as plus 2,500, and this one here is minus 2,500. Because the potential difference here would have still been the same, 5,000 volts between the plates with a certain separation there. So that's what we're going to start looking at here. So don't forget this is a uniform field, so it does have a uniform force on any charged particle put in there. So let's say we were to release an electron halfway between the plates here somewhere, like that. So what would the force on that electron be? Coming back to your definition of electrical field, it's the force per unit test charge, okay? So we can rearrange that to F equals EQ, which is quite a common thing to do. That's the electrical force on a charged particle in any electrical field. So here it's uniform. So in this case here, we would need to know the electrical field. Now this is not the electrical field 5,000. It's actually got a different sort of value here. We'll look at this later on how you get it, but the electrical field on the formula sheet there, it's the potential difference between two plates there, divided by the separation between the plates. How far apart are they? So looking at that, it's 5,000 as a potential difference between the two of them, divided by 0.10 metres. And if you do that, you get 5.0, actually by 10 to the 4. And I'm going to tell you it's a volt per metre in this case, but it is equivalent to a Newton per coulomb, okay? So that's the electric field. Now once you've got that, we can come and find the force on that electron here. So we're going to release the electron halfway there, what would happen? So looking at that, we've got 5.0 by 10 to the 4, and on the formula sheet there, you will find you've got 1.6 by 10 to the minus 19 coulombs of charge for a typical electron. Same for a proton, by the way, but it's actually positive. So looking at that, you've got 5 times by 1.6, you've got 8.0 times by 10 to the minus 15 newtons. So now that you've got that there, you found the force. If I want to start looking at equations of motion in here and treating it just like a projectile above the Earth's surface, I need to know the acceleration still, so I haven't got that yet. By the way, that force is going to be up towards the top plate because this is a negative charge and that's a positive plate. So to get the acceleration here, you're going to rearrange the F equals ma1 and do A equals F over m. So you can do this as 8.0 by 10 to the minus 15 divided by, now looking that up for an electron, not a proton, you're going to get that mass there on the formula sheet. And you get 8.78 by 10 to the 15, which is a huge acceleration compared to gravity. That's the acceleration downwards to this electron. So because of that, you can virtually ignore gravity in this situation, because gravity is only 9.8, and that gravity does act on the electron, but it's insignificant compared to that sort of size number. Now once you're up to there, you can go and treat this as normal equations of motion question there. They could ask you questions like, how long will it take to hit the plate, how fast will it be going, and so on. The other way to consider this, of course, is you could have done this in one go. You could have said, okay, every time I want the acceleration in a uniform electric field, I'm going to do EQ in place of F here over M. And that one equation will actually skip this first step and combine them together, and you can get it in one go. So you would actually get the same result by doing it that way. So that's extremely common to do it like that if you just want the acceleration in a uniform field, electric field. Okay? And once you've got this sort of stuff here, you're right to go, because this is now the same as the projectile motion questions you've done in the past. Once you have A, you can treat this the same way. So I could have asked you, how long will it take to hit the plate if I release it halfway, say? And you can just use your equation of motion. So just as a quick example of that, you could actually say, okay, the vertical velocity, or the velocity parallel to the electric field, is going to be 0 to start with because you're just going to release it in between the plates. It's going to travel down half the distance before it hits the plate. So half of 10 centimetres will be 5 centimetres, 0.05 metres. And we've actually got an acceleration here in that parallel plate direction. I should say in the direction parallel to the field, which is downwards in this case. So you can think of it as being like vertical. So I could have said to you, how long will that take? And you would use an equation of motion, the same as projectiles, to work that out. So you choose the one with that in there, S equals VAT plus a half AT squared, but of course there's no initial velocity. So all you're going to do is rearrange that. So if you rearrange it as a formula first, you'll get 2S over A. If you want to put the numbers in first, that's okay. But the square root here of 2S over A will be the square root of 2, 3.37 by 10 to the minus 9 seconds. Okay? So there's your time there, and that's a very short time period. But I could have said to you then, okay, what's the impact velocity there when it goes straight down? You would go and use VA plus AT, and that will tell you the velocity of the electron as it strikes that plate as well. So very much like the equations of motion, big difference here is you must find the acceleration first. It's not going to be 9.8. So let's just look at this as a process then. How similar to a projectile is it in a uniform gravitational field? So if you shoot charged particles like electrons into a vacuum of a uniform electric field, and this is a vacuum, don't forget, so the air resistance part of it and drag will not be a factor here. The electron will have no horizontal force acting on it if your plates are like this, because the electrical field is down vertically, and therefore horizontally in a vacuum, no forces, so no acceleration, so the velocity is constant in the horizontal direction. But the vertical velocity is going to undergo constant acceleration, and the reason for that is it's undergoing a constant force because the electric field is uniform, so therefore the force has to be uniform, the acceleration has to be uniform. So it's very much like the gravitational question. So just bear that in mind there. It'll be a parabolic curve then towards the positive plate if it's a negative charge, and towards the negative plate if it's a positive charge. All right, so just bear that in mind. So if you've got something like this here, this is a sort of typical electron gun situation here where they've actually got electrons leaving a cathode here, or a negative plate, going towards a positively charged plate, and it'll go through a hole or a slit, and that's what an electron gun does. And this here is the uniform electric field which is accelerating it. So you could work out the potential difference here and go from there. So a typical way of doing it is you would find E. So let's say you had an E here. This is not the one we're actually using. But the potential difference that you had, which would be 380 in this case, divided by the distance between the plates, would tell you the electrical field. Okay? Once you have the electrical field, you can find the acceleration here between this pair of plates. A equals EQ over M, and it's not the same as gravity. It's huge. All right. Once you're there, you can work out anything. How fast does it actually leave this slit here? You know, V equals VA plus AT. How long does it take to get there? So you could do that. All right. So the equations of motion pretty much are the same as the projectile motion that you've used before. It'll be more complex than that though, because this will come in at a certain speed then, and then they'll give you a uniform field here that it's crossing. Okay. So here the uniform field is down, 9 volts of potential compared to 0. And this is a negative charge, it's going to curve up, and it might actually hit this plate, or it might actually pass through with just a deflection and get to the other end. And you could be told the length of the plates there. All right. But the key thing here would be to find out the electrical field, then the acceleration, and then off you go. So this particular one is telling you the field 9 volts as a potential difference, 0.02 is the separation, here's the field strength. Therefore that's the acceleration of the electron. And once you've got that, you could then work out, well, how long does it take to get to here if I know the speed, or if it deflected and hit the plate, how long would that take, how fast would the impact velocity be. So it's very much like a projectile. So here's a typical example of a uniform electrical field here, where we've got an electron gun that's actually shot the electrons out. So you've got a heated filament here that warms up a metal plate or a cathode. That actually ionises the electrons by thermionic emission because of heat. Therm means heat, ionic means to ionise. So the electrons are sitting on that plate. You then set up that as a negative plate and another plate across here as a positive plate with a slit in it. Okay? And so the electrons will be shot across there as an electron gun in a vacuum. The electrons will come through here then at a constant speed, hit this fluorescent screen, and lights up the screen because it's actually blue. So that's what you've got here. And it's slightly angled, so you can see a whole line there. It's actually hitting from a slit a range of parts there. So you could actually deflect this using the positive plate at the top and the negative at the bottom, which will turn on now. We can deflect that and turn that up. Okay? So it's going towards the positive plate with electrons coming across. So that's going to follow a parabolic path, okay? And you could actually get to hit that top plate if it's strong enough and so on, so it goes like that. And then we could do calculations of this uniform electric field with the charged particles moving through there. This is the sort of thing you do in a TV, by the way, moving this around with either electrical fields or magnetic fields. So there's lots of devices that use this now. You could move this around equally by putting a magnet there and moving it around as well, okay, up and down. So magnetism can also move charged particles around, and we're going to look at that later next term. If we actually change this to make it a bit harder, we're going to fire the electron in halfway between the plates with the speed of 2 × 10⁷ meters a second. It's coming in parallel there to the actual plates. So at 90 degrees to the field, because the field's going down, the electron will have a force going up. And let's say it's going to deflect and hit the plate. So they could ask you questions like, how long does it take to hit the plate there? And what's its final velocity when it hits the plate? Same as we would have done with projectiles. So as a routine then, as I said, I'll be doing, okay, we need to find A equals EQ over M. Now unfortunately here, they have not told us the electric field. So as I said, there is a formula for that to find on the formula sheet if it's not given to you. So you're going to be doing 5,000 divided by 0.10, and you'll get 5.0 by 10⁴. And I've done two significant figures here to match that one. So that will be in a volt per metre, because they're the two you're dividing, volts and metres. But that's the same as a Newton per coulomb. Okay. All right. So looking at here, this is the same question as before. Basically, you've got 5.0 by 10⁴ times by the charge on the electron, same as a proton, over the mass of an electron, which is a big difference. So just bear in mind that the force on a proton and an electron is the same. But the acceleration is not, because the electron's got a tinier mass compared to the proton. So it's going to have more acceleration. And if we do that, we get 8.0 by 10⁵. Okay, meters per second squared, and it's going to go up. So there's your first step. All right. Second step then is you can start working out some questions here. All right. So that first, onto acceleration, and from here on, we're doing it the same way as you would have done other questions. So looking at that then, that's 0.10 there, terrible diagram. You would actually find, say, the time that it takes to hit the top plate. So what's the time going to be here, if that was the first question? So based on that, we've got a VO in the vertical direction, or the direction parallel to the field, of 0. We know the acceleration. It's not minus 9.8, it's 8.0 by 10⁵. And we've got a displacement, because it's halfway through the plates here, so we're going to displace 5 centimetres again. Now if you look at that, this is exactly the same question as before. How do we find time in the last one when we just released it here and let it go that way? It'd be exactly the same as if you fire it in, because the horizontal and vertical components in projectiles are independent. It's the same here. The parallel components and the vertical components are independent of each other, so just remember that. So here we did last time S equals a half AT squared, because we dropped the VOT. We don't need the VOT here because it's 0. Okay. And we rearranged the T equals root 2S over A. And that gave us a time of 3.37 by 10⁻⁹ seconds from memory. Okay. So we know the time it takes to hit that plate. So we could again now continue on and work out what the vertical velocity would be when it hits the plate. The final velocity there. So V would equal VA plus AT. Again, the VA is not going to give us a problem there. You're going to do 8.0 by 10⁵ times by 3.37 by 10⁻⁹. And we'll actually work out what the velocity that way is when it strikes the plate in meters per second. And it was 2.96 by 10⁷ meters per second. So we now know the velocity vertically. So if you wanted the total velocity when it strikes, it's coming in like this, isn't it? So what you've got is two components there. You've got a component that's actually perpendicular to the actual field, which is 8 by, no it's not. It starts off as 2 by 10⁷, doesn't it, when it comes in? That's what I told you at the start. There, yep, 2 by 10⁷. And we now know that it's actually gained a velocity vertically in the vertical component of 2.96 by 10⁷. So to work out the velocity there, you're just going to do your Pythagoras, same as before, square root of, and that'll give you the size of the velocity of the speed. You could get the angle as well if they ask you what is the velocity, in which case you can do theta is 10⁻⁴ of 2.96 over opposite over the adjacent. And I've cancelled out the times 10⁷ parts. Okay? So they're the sort of questions you can do. You can do projectiles in an electrical field because it's uniform forces, and so on. Thanks.